Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 9th, 2026, about 5 days ago. It introduces a reinforcement learning framework that drastically improves how video world models follow instructions, boosting accuracy on complex actions from just 20% to over 55%. The paper is titled WorldCompass, Reinforcement Learning for Long Horizon World Models. And as we'll see later, the implications for creating consistent, interactive virtual environments are really significant. Figure 1 illustrates the complete WorldCompass pipeline, which splits the post-training process into 3 distinct stages. On the left, the system starts with a shared history of video clips and performs a clip-level rollout, generating multiple candidate futures for a single target step. These candidates are then scored by the reward functions shown below, which assign values like plus 0.8 or minus 0.7 based on action adherence and visual quality. Finally, on the right, an efficient reinforcement learning algorithm uses these signals to update the model, mathematically steering it toward the best outcomes. So, Figure 1 outlined the pipeline, and now Figure 2 demonstrates how effective it is during training. These charts track the model's progress on 2 key metrics over 50 training steps. On the left, action accuracy climbs dramatically, starting near the base world play level of roughly 27% and reaching nearly 73%. Meanwhile, the right panel shows the visual quality score, measured by HPSV3, improving from 1.66 to 2.56. This simultaneous rise confirms that the complementary reward functions successfully steer the model toward both better instruction following and higher visual fidelity. So, while Figure 2 showed the learning curve, Table 1 breaks down the final performance numbers. It compares 2 base models, Hunyan Video 1.5 and WAN 2.2, across short, medium, and long-term horizons. Focus first on the combined action results in the left columns. In the short-term section, the Hunyan model improves its action accuracy from roughly 22% to 58%, a massive 36-point jump. This gain persists in the midterm section, where the accuracy increases by over 35%. At the same time, the HPSV3 scores rise, confirming that visual quality actually improves alongside control. Well, Table 1 gave us the hard numbers, but Figure 3 shows what that actually looks like in practice. This figure compares generated video sequences for complex combined actions, with the base model in the first and third rows, and the WorldCompass version in the second and fourth. Look at the top tropical island scenario. The base model largely ignores the W&A command, keeping the frame static. In contrast, the WorldCompass row below it clearly moves the camera forward and to the left, adhering to the composite instructions. The same improvement is visible in the bottom sci-fi example, confirming the accuracy jump. So, Figure 3 just showed the visual results, but Table 2 performs an ablation study to pinpoint what actually drives those gains. Row 0 establishes the baseline with no reinforcement learning, where combined action accuracy sits at roughly 20%. In contrast, Row 1 shows the full WorldCompass setup, which boosts that accuracy to nearly 55%. Crucially, Row 2 proves the necessity of the clip-level strategy, as switching to sample-level rollout causes performance to crash to 12%. Finally, Rows 3 and 4 confirm that removing either reward signal significantly degrades the results. While Table 2 analyzed the core components, Table 3 evaluates the efficiency strategies. It specifically tests 2 optimization techniques, using a subset of time steps, and best-of-n sampling. Looking at the iteration time column on the right, the top row represents the fully optimized approach, which serves as the baseline speed. The bottom row shows that removing both optimizations slows the process down significantly, increasing the time to 2.26 times the baseline. However, the action accuracy column in the center remains steady around 55%, proving that these massive speed gains do not compromise the model's performance. Alright, moving from efficiency numbers to spatial understanding, Figure 5 visualizes the model's actual movement in 3D space. The goal here is to execute AW plus A command to move forward and left, followed by a right turn. On the left, the base model produces a trajectory that looks ambiguous, failing to clearly commit to the directional changes. In contrast, the WorldCompass result on the right shows a decisive, well-structured path that adheres to the composite instructions, while also maintaining a more consistent 3D scene structure. Wrapping up, 2 takeaways stand out. Reinforcement learning is highly effective for post-training video models, and efficient strategies like clip-level rollouts are key to making it work. This paves the way for reliable, long-horizon interactive environments in gaming and simulation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.